Hello everyone, my name is Deep, and the paper that I'm going to talk about that is related to the radio frequency MAM switch used for the reconfigurable antenna. Before going into the details, I want to talk a little bit about the reconfigurable antenna as well as about the radio frequency MAM switch. So reconfigurable antenna has recently received a great attention in the recent communication systems because a single reconfigurable antenna can be used to change the operating frequency, radiation pattern based on the different application requirements. And radio frequency MAM switches can be equipped with antenna design to make it reconfigurable by changing its geometrical structure for different resonance frequencies. So in the left side, you can see a picture which is actually represents the common design and of the RF MAM switch, and you can see here the MEMS bridge, and below that there is a thin dielectric layer, and below it the electrode. So when voltage is applied between the electrode and this MEMS bridge, then electrostatic force is induced on the switch beam, and the beam operates as a parallel plate capacitor. So when switch beam is in the upper state, then the transmission line experiences a small capacitance, and when it is in the down state, the transmission line experiences a high capacitance. In order to optimize the performance of the switch, it's very important to choose the proper material for this MEMS bridge. And this paper is mainly dealt with that material selection technique as well as to select the proper material for this to optimize the performance of the RF MEMS switches. So I'm going forward. Here is the title of the article, and that is the material selection of RF MEMS switch used for the reconfigurable antenna using HB methodology. And below that, those are the name of the authors, and the article was published in the Progress in Electromagnetic Research Letters in 2012. So in the specific scope of the study or this article is that they provide a proper technique to select the best possible material that is needed as a bridge material in the RF MEMS switches. As I mentioned earlier, that the device performance or switch performance, the performance of the switches mainly depends on the bridge material. So in this article, they provided a specific techniques, and that is actually the HB material selection technique to select the best possible material. And the key question that is addressed in this article is that how much the HB material selection strategy is effective to select the best candidate material for RF MEMS switches. So I'm going forward. In the methodology section, the methodology they used here, that is the HB material selection strategy or HB methodology. And material performance indices, there are 5 material performance indices. So, and they are Young's modulus, electric resistivity, Poisson's ratio, thermal expansion coefficient, and thermal diffusivity. And in the introduction section, they didn't talk very much about the other material selection strategies. They just mentioned that several material selection strategies has been used in other articles, but this is the first time that material selection tool is used for the RF MEMS switches, and they used the HB methodology here. So they didn't talk about lots of the other material selection strategies is in the introduction section of the article. So going forward, so before going into details of the result, the performance index X, there are 3 performance index X for the RF MEMS switches, and the first one is the pull-in voltage. And if you see here, this is the equation of the pull-in voltage, and from the equation we can see that the pull-in voltage is dependent on the spring constant K, where the spring constant K is also dependent on the Young's modulus, and in the third equation The spring constant K is also dependent on the Poisson ratio, that is nu, and the thermal stress. So at first they plotted the graph, which is thermal expansion coefficient versus Poisson ratio. So here in y-axis thermal expansion coefficient, and in the x-axis that is the Poisson ratio. So from this plot, they look for that material where the thermal expansion coefficient is high and the Poisson ratio is also high. And they found that there is a trade-off between the aluminum and the gold, because in case of the aluminum, and the thermal expansion coefficient is the highest, but Poisson ratio is not the highest. But in case of the gold, the Poisson ratio is the highest, but the thermal expansion coefficient is not the highest. So from this plot, they have concluded that aluminum and gold can be the best candidate for the bridge material based on this graph. And the third plot, that is related to the Poisson ratio as a function of the Poisson ratio versus Young's modulus. So here they're looking for that material for which the Young's modulus is very low, and they found that the gold and the aluminum, they have the lower Young's modulus and they have also high Poisson ratio. So, and they have concluded that based on this plot, the gold and the aluminum are the best material to reduce the pooling voltage because of their high Poisson ratio as well as the lower Young's modulus. Going forward, and the second performance indices, that is the thermal stress. And the thermal stress, this is the equation of the thermal stress, and the thermal stress is actually dependent on the thermal expansion coefficient. And the third performance indices, that is RF loss. And the power loss or RF loss, this equation is the I squared dot R. So here we will deal with the two types of the resistance. One is the thermal resistance and another is the electric resistance. And they have showed that the multiplication of the thermal resistance and the electric resistance, that is equal to the electric resistivity divided by thermal conductivity. So based on this equation, they said that they were looking for that material for which the electric resistivity is low and the thermal conductivity is high. And for this, at first they plotted the electric resistivity versus Young's modulus. So since they were interested in the less Young's modulus and the less electric resistivity, so they concluded that aluminum and the gold show the which showed the minimum value of the Young's modulus and the electric resistivity, and those materials are good for the minimum RF loss. And in the third plot, which is electric resistivity versus thermal conductivity, and since they were interested the materials whose have higher thermal conductivity, so they mentioned that gold and the copper followed by the aluminum provide the minimum thermal residual stress because they have the low thermal electric resistivity and also high value of the thermal conductivity. So they concluded that the gold and the aluminum both can be the best materials for the best candidate material as for the bridge material. So going forward, so now I have come into the conclusion. The first one is that yes, that I mentioned earlier, they have applied the HB approach for the material selection, and the HB approach they have discussed the principle of this approach and how they used it to select the material for the RF capacitive shunt switch. And the second point is that based on all of the plots and based on all of the results and the relation between the performance indices and the material index, gold and aluminum are the appropriate materials. But if we think about from the point of cost, the aluminum is proposed as the best material over the gold because it is less expensive than the gold. So in the end, they concluded that that aluminum will be the best candidate for the bridge material of RF MEMS switch. So my personal critique regarding this article is that this article is very well written and well organized, and but they didn't mention so much about the other material selection strategies, because they talked a lot about the HB approach, the approach they use. And second point in my thinking is that here they deal with all of the metals or the ceramic materials. But if we deal with only the composite or the natural materials, which are cost effective and environment friendly, and also some of them have the good qualities or good properties than the metals and the ceramic materials, then what will be the best composite materials for the RF MEMS switches? So that's all. Thanks.